Dipole moment. Dipole moment. What is this dipole moment? Where it is applicable? What are the applications of this dipole moment? For what purpose this dipole moment is introduced? Before going to take this dipole moment, you should know about the polarity of the molecule. Polarity of the molecule. See here how. That is, let us take a bond between two similar atoms. That is a covalent bond between two similar atoms. Here hydrogen and hydrogen, both the atoms are same. Both these have same electronegativity. So this is the bond pair. This is the bond pair of that hydrogen bond between those hydrogens. So this hydrogen has electronegativity. This hydrogen has also electronegativity. Both these electronegativities are same. That's why this is strongly attracted by this hydrogen. At the same strength, this hydrogen is attracted, and that means this electron pair is exactly middle between these two atoms. Because of that, no one loses electrons, no one extra gains electrons. Because of that, no one gets positive charge, no one gets negative charge. But in case of a bond is present between hydrogen and chlorine, here electronegativity of chlorine is 3.0 and hydrogen is 2.1. These are the electronegativities. Now this is the bond pair, boys. This is the bond pair. So more electronegative elements strongly attracts that electron pair than that of less electronegative element. That is why this bond pair is strongly attracted by the chlorine but weakly attracted by hydrogen. That means unequal attractive forces are there. But here equal attractive force. Here unequal attractive forces are there. Unequal attractive force. Because of this unequal attractive forces, this chlorine gets partial negative charge and hydrogen gets partial positive charge. But not here. No one gets positive charge, no one gets negative charge. But here hydrogen gets positive charge and chlorine gets negative charge. Those charges are very, very less charges, and that is partial charges. Because this electron pair is slightly moving towards chlorine, not completely entered into the chlorine. Because of that, partial charges are developed. Okay, a bond with partial positive and negative charges are called as a polar bond. Polar covalent bond. This HCl bond is a polar covalent bond. But here no positive, no negative. That's why it is a non-polar covalent bond. A non-polar covalent bond. That is a polar covalent bond. This is a non-polar covalent bond. No charge separation is here. No charge separation. No charge separation is possible. But here, charge separation is there. Charge separation is there. So because of this charge separation, positive and negative charges, because of this charge separation, this is polar bond. This is polar bond. So here, this is called as, this chlorine gets partial negative charge, this hydrogen gets partial positive charge. Okay, this is called as negative pole. Negative pole. This is called as positive pole. Hydrogen gets partial positive charge, that is why that is partial positive pole. Chlorine gets partial negative charge, that is why that is called as negative pole. That means in this molecule, in these molecules, two poles are there. Two poles are there. One is positive, one is negative. Two poles are there. Those two poles are considered as, two means a diend. Two means a diend. That's why it is called as a dipole. That's why it is called as a dipole. Therefore, HCl molecule has a dipole. Therefore, HCl molecule has a dipole. What is dipole? Splitting up that bond into partial positive and negative charges. That creates two bonds, two poles, which is called as a dipole. Less electropositive element, less electronegative element gets partial to positive charge. More electronegative element gets partial negative charge. That is called as a dipole. Okay. So now our dipole moment is applicable for this dipole concept. That means this dipole moment is applicable for a polar molecule, not for a non-polar molecule. That means a covalent bond is formed between two dissimilar atoms that gives a polar covalent bond. So in that polar covalent bond, this dipole moment concept is applicable. Okay, so where dipole moment is applicable? In a polar compound. In a polar compound. Which one is a polar? In a polar covalent bond. Which one is a polar covalent bond? That means a covalent bond existing between two different atoms. Existing between two different atoms. That is a polar covalent bond. Whenever polar covalent bond is there, there should be a dipole moment. Now we are entering into the dipole moment. So for explaining this dipole moment, we consider a polar covalent. We must consider a polar covalent bond because there only dipole exists. There only dipole exists. Now, dipole moment. What is this dipole moment? Which is indicated with the letter symbol mu. Dipole moment, the symbolized with mu. Mu is equal to dipole moment. What is dipole moment? Let us consider a polar covalent bond. That is, I am taking HCl, boys. It is HCl. This hydrogen gets partial positive charge. This chlorine gets partial negative charge. This partial and positive and negative charges is due to the unequal sharing of this electron pair. That means this bond pair of electrons slightly moving. That means nearer to the chlorine and away from hydrogen. Slightly nearer to the chlorine and away from hydrogen. That is why chlorine gets negative charge, hydrogen gets partial positive charge. Okay, it is due to mobility of movement of this bond pair towards high electronegativism. Because of this, so from where to where the electron pair is migrated, was shifted, moved. That means from positive pole to negative pole. So towards negative pole, the electron is attracted. That means here the electron's direction is like this. Electron's direction. Bond pair of electrons are attracted like this. That means so from positive end to negative end. This electron pair actually this is adherent, but it is slightly moved like that. Because of that, this one gets positive, this one gets negative. Partial positive and partial negative. So a moment end, because of that moment, from where to where, positive to negative end. That moment is called as dipole moment, bond moment. So dipole moment is indicated with the letter symbol, an arrow with a cross at the tail part. It is the symbol for dipole moment. It is the symbol for dipole moment. An arrow, a cross at the tail part is the symbol for dipole moment. Is the symbol for dipole moment. Okay. Now, so how to calculate dipole? Boys, here is there any direction for this dipole moment? Direction is there or not? Yes, there is a direction. In which direction? From positive to negative. That is the direction. So electron migration, electron shifting from positive to negative. That means dipole moment, this concept has a direction. It has a direction, boys. And also it has a magnitude value also. It has a magnitude value because any concept, any topic, any concept having both direction and magnitude, that property is called as a vector property or vector concept. So therefore, dipole moment we consider as a vector quantity. Dipole moment we consider as a vector quantity because it has direction. What is the direction? From positive to negative. So dipole moment has a vector quantity. It has something magnitude there. So how to calculate that magnitude of the dipole moment? It has something magnitude. That means dipole moment has both direction and magnitude. Therefore, it is considered as a vector quantity. Now I want to find out the magnitude of this dipole moment. Magnitude of this dipole moment. So dipole moment is calculated. See, boys. So dipole moment mu is equal to. Here something charge is separated, boys. So that is the partial charge ending. That charge into the distance between these two poles. Between these two poles, something distance, that is, let it be L. What is L? It is the distance between two poles. What are those two poles? One is positive pole and negative pole. So this is called a distance between the poles, which is called as internuclear distance. Internuclear distance, which is also called as bond length, which is also called as bond length. So internuclear distance or bond length, which is called as distance between the two poles. So this is multiplied with that L value. So this is the way to calculate dipole moment value. Dipole moment mu is equal to, what is this formula, boys? Mu is equal to charge into length, which is nothing but charge into length. Dipole moment mu is equal to charge into length. Charge into length. So generally, charge is also expressed in terms of, boys, in some examples, some books, charge is expressed with Q and distance is expressed with L, and Q into L also called as dipole moment. Q is nothing but charge. Q is nothing but charge. So, but I'm using delta. I'm using delta. So this is mu is equal to delta into L, that is charge into length. Charge into length. Now, what are the units of this dipole moment? What are the units of dipole moment? Now, what is the definition for this dipole moment? Before going to that, I can define this dipole moment. So, what is this dipole moment? That is, a dipole moment is the multiplication value, that is nothing but product of magnitude of charge, product of magnitude of charge on dipole and distance between the poles. In a polar covalent bond. So it is the product of magnitude of charge and charge on dipole and one of the poles. On one of the poles and the distance between the poles in a polar covalent bond. That is dipole moment. That is nothing but charge into length. So it is symbolized with mu is equal to delta into L. Mu is equal to delta into L. It is the formula to calculate magnitude. It has direction. That is, it has a direction, boys. That is positive to negative. It has direction. That means this is the symbol, positive to negative. So that means it has both magnitude and direction. Therefore, dipole moment is a vector quantity. It is a vector quantity. Now, what are the units of this dipole moment? What are the units of this dipole moment? See here. Units. What are the units of this dipole moment? Mu is equal to, our formula is charge into length. So I'm trying to explain in MKS system. In MKS system, that is nothing but SI system. In SI system, so mu is equal to charge is expressed in terms of coulombs. Charge is in coulombs and length is in meters. So coulombs and meters. Therefore, the unit is coulomb meter is the unit. Coulomb meter is the unit for this dipole moment in SI system, boys. In SI system, the unit is coulomb meter. But so in CGS system, charge is expressed in that is ESU units. ESU means electrostatic units. Charge has ESU units and centimeters is the unit for distance. That means that is ESU centimeters is the unit in case of CGS system. In CGS system, the unit is ESU centimeters. In SI system, the unit is coulomb meter. So these are the units. Finally, units is coulomb meter or ESU centimeters. Coulomb meter or ESU centimeters. Those are the units of this dipole moment. But the frequently used unit for this dipole moment is not both of those. So the frequently used unit is, but it is SI unit, it is a CGS unit. But the common unit of mu is equal to d by n. The common unit of mu is equal to d by r. D by is the frequently used unit. What is this d by, sir? So this d by in terms of Coulomb meter and ESU centimeters we will derive it. See here, mu is equal to charge into distance, length, distance, that is length, and charge. Generally, see boys, I am taking HCl molecule. Here delta plus, delta minus. Why that gets negative charge? Minus 1, why it is 1 extra electron is coming out. That means the charge is due to 1 electron. Electron has charged. How much is the charge? In coulombs, electron has charge 1.602 into 10 power minus 19 coulombs. Therefore, charge is equal to, for example, 2 electrons are transferred, minus 2 will get. 3 electrons are transferred, minus 3 is get. That means we want only magnitude, not that minus. That is why something value into, that is 1, 2, 3 into 1.602 into 10 power minus 19 coulombs. It is the charge. It is 2, 3 like that. Into distance. Generally, distance is expressed in terms of angstrom units because in short way angstrom. But we must use in meters. 1 angstrom is equal to 10 power minus 10 meters. That means, for example, y angstroms is the distance between them. That is equal into y into 10 power minus 10 meters. Therefore, by multiplying this time, that is x into y into 1.602 into 10 power minus 19 into 10 power minus 10. That is coulombs. This is meter. So this is the way to calculate it. So 10 power minus 10, 10 power minus 19, which is equal to 10 power minus 29. 10 power minus 29. By adjusting, it is 10 power minus 30, like that. 10 power minus 38. Okay, that means it is in terms of 10 power minus 30 units. That means 1 dBi is equal to 3.33 into 10 power minus 30 Coulomb meter. It is a conversion. It is in terms of Coulomb meter. 1 dBi is equal to 3.33 into 10 power minus 30 Coulomb meter. 10 power minus 30 Coulomb meter. But in terms of ESU centimeters, how much is that? ESU centimeters. Use those values in terms of ESU centimeters. It is of the order of 10 power minus 30 Coulomb meter. But in case of ESU centimeters, that is charge. 1 electron charge 4.8 into 10 power minus 10 ESU into distance angstroms. 1 angstrom is equal to 10 power minus 8 centimeters. So something y into this much, x into this much. And therefore, x into y into 4.8 into 10 power minus 10 into 10 power minus 8 ESU centimeters. So 10 power minus 10 and 10 power minus 8, which is equal to 10 power minus 18 ESU centimeters. This 10 power minus 18 ESU centimeters is equal to 1 dBi. So therefore, 1 dBi is equal to 1.0 into 10 power minus 18 ESU centimeters. This is the conversion. If centimeters are given to you, say Coulomb meter is given to you, convert into dBi. dBi into Coulomb meter. That is ESU centimeters to dBi. dBi to ESU centimeters. So these are the conversions. So the common unit for dipole moment is dN. That is dBi. That is dBi. So 1 Coulomb meter is equal to 3 into 10 power 29 dBi. 1 Coulomb meter is equal to 3 into 10 power 29 dBi. So these are conversions, boys. but frequently used unit is this one. Frequently used unit is this one, that is debye units. Debye units. So this is about your dipole moment, boys. So what is dipole moment? It is a product of charge and distance between the poles. So what are its units? Debye units common, but MKS unit, coulomb meter, CGS unit, ES centimeters. So these are the conversions. These are the conversions. One debye is equal to 1.0 into 10 power minus 18 ESU centimeters, or 1 debye is equal to 3.33 into 10 power minus 30 coulomb meter. So this is the conversion. So by using these, we have some problems based on that. So see here. So this is dipole moment. Sir, okay, dipole moment is explained. Now, why, sir? Why this dipole moment is used? What are the applications of this dipole moment? Now, this is very, very important topic in your chemistry. This dipole moment is very, very helpful to predict whether the molecule is polar or non-polar. Whether the molecule is polar or non-polar, this is the most important concept. So that is the most important application of this dipole moment. See here, how? What are the applications of this dipole moment? Where this dipole moment is exists, which if exists, which one is more, which one is less? Okay, so now characteristics of this dipole moment. Characteristics of dipole moment. Where it is more, where it is less. Characteristics of dipole moment. Dipole moment for some molecules may be equal to 0 or not equal to 0. If a molecule is a symmetric condition, molecule has a symmetric structure, there mu is equal to 0. Molecule has a symmetric structure, there mu is equal to 0. Molecule has non-symmetric structure, mu is not equal to 0. Non-symmetric, mu is equal to not equal to 0. See boys, that is first point. For symmetric molecules means linear structure, that is trigonal planar structure or tetrahedral structure, octahedral structure. These are the symmetric structures, boys. Linear, trigonal planar, tetrahedral, octahedral. These are the symmetric structures. If molecules have these structures, their mu is equal to 0. Their mu is equal to 0. Okay, symmetric structure. Even the molecules have polar bonds. If for molecules, symmetric molecules, even though so they have polar bonds. Even though they have polar bonds, mu is equal to 0. For example, let us take an example. See boys, that is BeCl2. BeCl. So beryllium chloride. It has linear molecule shape. It is the shape. Okay. See boys, among this in this bond, so chlorine is more electronegative than beryllium. Therefore, chlorine gets partial negative charge, beryllium gets partial positive. Now, what is the direction of this dipole moment? That is positive to negative. So, this is the direction of that dipole moment. This is the direction of dipole moment. So, that is, I am taking this one as plus mu. Plus mu. Now, here, this chlorine also gets partial negative charge. This one partial positive, that is partial plus finally. Now, this is positive, this is negative. It is the direction of this bond dipole moment. Every bond has dipole moment, boys. So this is direction, this is direction. Both these are opposite. That's why it is minus mu, boys. That's why it is minus mu. It is plus mu. Now overall, mu is equal to this one plus this one. Here magnitude between beryllium and chlorine, mu ra. Beryllium, chlorine, mu ra. But it is plus, it is minus. Total mu is equal to 0. Total mu is equal to 0. Boys, it is a polar bond. It is also a polar bond. That means this molecule has polar bonds, but mu is equal to 0. That means overall this molecule, final molecule is non-polar molecule. That means those molecules have mu value is equal to 0 are considered as non-polar. So these are non-polar. Even though molecule has a polar bond, because it is plus mu, it is in this direction, it is in this direction. Exactly magnitude value is same, but opposite in direction. That's why these values are cancelled. Therefore, final mu value is equal to 0. Final mu is equal to 0. So it is linear case. So in case of linear, so mu is equal to 0 because it has symmetry. Next, I am taking one more example, boys. I am taking one more example, that is BCl3. BCl3. BCl3 means this is molecule trigonal planar structure. This is BCl3 molecule, boys. Here chlorine is more electronegative than boron. That is why the dipole moment of this bond is in this direction. This bond is in this direction. Positive to negative. Positive to negative. Okay. Now, see boys, because these are vectors, resulting vectors is in this direction. This is like this, this is like this. The resulting vector is like this. Am I correct? You know vector quantity, vector summation, vector conditions. So this is direction, boys. The resulting vector is like this, resulting vector. So that means here with boron with chlorine, in exactly opposite direction there is a vector. There is a vector. So these two magnitudes are same. This one is cancelled with this one. It is plus mu, it is minus mu, cancelled. Next, these two resulting vector is in this direction. These two resulting vectors in this direction. So exactly opposite there is a same magnitude and it is plus mu, it is minus mu, cancelled. These two resulting vector in this direction, boys. In this direction. This one and this one are cancelled. That means overall the mu value is equal to 0. Overall the molecule has a mu is equal to 0 and therefore BCl3 molecule is a non-polar molecule. BCl3 molecule is a non-polar molecule because it has a symmetric structure, that is trigonal planar shape. So linear molecule, trigonal planar molecule, tetrahedral. Adi kuda chuddam okasari. So that means BCl3 is a polar molecule or non-polar molecule. So that is the molecule having polar bonds. Finally, it is a non-polar because its mu value is equal to 0. It is a non-polar molecule. It is a non-polar molecule. Now I am taking one more example. That is CCl4 molecule. Carbon tetrachloride. CCl4 molecule. Now this is carbon. These are 4 chlorines, tetrahedral, boys, not in same plane. Not in same plane. Okay. Now, so carbon chlorine, which one is positive, which one is negative? Carbon positive, chlorine negative. Right? Therefore, this bond is dipole moment in this direction. This bond has this direction. This bond has this direction. This bond has this direction. Boys, see, observe here. So this is almost pyramidal, like this, like this. Okay, this is one dipole, this is another dipole, this is another dipole. The resulting dipole is like this, downward direction, resulting direction. That means these three dipoles resulting is in this direction. Resulting is in this direction. Exactly opposite direction there is n. That means these two values are cancelled. So next, these three is this direction, exactly opposite. So like this, resulting mu value is equal to 0. Therefore, there is a polar molecule. This is, see here, there is polar bonds. CCl bonds are polar end. But overall the molecule, because mu is equal to 0, is a non-polar end. That is why CCl4 molecule is a non-polar molecule. CCl molecule is a non-polar molecule. That is why CCl4 is generally used as a solvent boys. So CCl4 is considered as non-polar solvent. Non-polar solvent. Benzene also non-polar. Mu is equal to 0. Mu is equal to 0. So that means it is used to predict whether the molecule is polar or non-polar with the help of this pattern. Even though molecules have polar bonds, sometimes mu may be equal to 0. So mu is equal to 0, that is non-polar. If mu is not equal to 0, that is polar. So see here, where mu is not equal to 0. So let us take an example. That is NH3. Ammonia has a pyramidal structure and a lone parent. This is ammonia. This is ammonia. Among this nitrogen and hydrogen, which one is positive, which one is negative? Nitrogen is more electronegative, that's why this one gets negative charge, this one gets positive charge. Therefore, this has positive to negative. This is positive to negative. This is positive to negative. Okay, so that means this is the pyramidal boys. This is. Altogether, the resulting value is like this. This is resulting vector. This is resulting vector direction. So there is a lone pair, boys. Always lone pair. Lone pair also creates dipole moments. Dipole moments. Always away from the atom. Away from the atom. This is from lone pair. This is from NH bonds. These two are in the same direction. That means not cancelled. Both are added, boys. That means mu is enhanced automatically, not equal to 0. Both are in the same direction, not cancelled. Not cancelled. Enhanced mu value. That means mu is not equal to 0. Therefore, NH3 is a polar molecule. So its mu is not equal to 0. Its mu is not equal to 0. Next, similarly, NF3, we will consider NF3. What is that NF3? NF3. This is NF3, boys. This is NF3. Among nitrogen and fluorine, which one has more electronegativity? Among nitrogen and fluorine, which one has more electronegativity? Fluorine is more electronegative, nitrogen is less electronegative. That's why nitrogen gets positive charge, fluorine gets negative charge. Our target is positive to negative. That means this is the direction of dipole moment. This is the direction of dipole moment. This is the direction of dipole moment. That means these three resulting dipole moment is like this. Resulting. Now lone pair away from the atom. Lone pair has this much. These magnitudes are not same, but opposite in sign. Something value, because it is I am taking this one as minus 50, this is plus 20. Plus 20 minus 50, something minus 30 is there. That means value is not becomes 0. That means here also mu not equal to 0. But when compared to this, why not equal to 0, sir? Because it is due to lone pair, it is due to NH. That means because it is positive, I am taking this one as negative, but magnitude value, here also magnitude. These magnitudes are not same. These magnitudes are not same. Because it is with nitrogen fluorine, but it is with lone pair. For example, if it is like this, here also fluorine is there, here also fluorine is there, automatically cancelled. But it is with lone pair, That is why magnitude is not same, even though opposite in direction. That is why mu value something cancel not becomes 0. Something cancel not becomes 0. Therefore, mu is not equal to 0. See, boys, among these two examples, that is, this is let it be first example, this is a second example. Which one has greater mu value? Which one has greater mu value? First one or second one? Yes, that means mu NH3 greater than mu NF3. Mu NH3 greater than mu NF3. Absolutely, you are correct, boys. Okay, therefore ammonia is a polar molecule or non-polar molecule. It is a polar molecule. NF3 is also a polar molecule, but the polarity of NF3 is less than that of polarity of NH3. That means polarity of the molecule is explained on the basis of this mu value. Finally, we concluded that this dipole moment is useful to decide the shapes of the molecule. Dipole moment is useful. Therefore, mu is used to predict the shapes of the molecules. Mu is used to predict the shapes of the molecules. See boys, if a molecule of AB2 type, so maybe its mu is equal to 0 or mu not equal to 0. If mu is equal to 0, the molecule has linear shape. Example, CO2, BeCl2, etc. CO2, BeCl, that is AB2 type molecule. Now it is mu not equal to 0. The molecule has bent shape or angular shape. That means H2O, SO2 like molecules. H2O, SO2 like molecules. All those are AB2 type molecules, boys. So here mu not equal to 0 means these are polar. Mu is equal to 0 means these are non-polar. Okay, non-polar molecules have linear shape and polar molecules have bent or angular molecule shape. Next, if a molecule of AB3 type, so mu is equal to 0 possible and mu not equal to 0 possible. Mu is equal to 0 means non-polar. Mu not equal to 0 means polar end. So this type of molecules, that is trigonal planar. Already I explained, boys. Trigonal planar shape. That means the best example for that one is BCl3, SO3, etc. BCl3, SO3, etc. Next, mu not equal to 0. That means NaH3, NF3, NBr3, BH3, like this. All these molecules, AB3 type molecules, mu is not equal to 0. All those are polar molecules. So the shape is pyramidal shape. For these, shape is pyramidal. For these, trigonal planar shape. Okay, AB3 type, mu is equal to 0, trigonal planar. AB3 type, mu not equal to 0, pyramidal. That means this is the way to predict the shapes of the molecule. Next, one more. Next, AB4 type molecule, boys, mu is equal to 0, mu not equal to 0. It is non-polar, it is a polar end. So, which has tetrahedral shape. It has distorted tetrahedral end. Distorted tetra. That means all bond angles are not accurate. All are not 109 degrees 28. So values are changed. But here all values, all bond angles are 109 degrees 28 minutes. All bond angles are same. That is symmetric. So that means the example for this one is CH4, CCl4, C6, so not CH, CCl4 like this molecule. CH4, CCl4 like that. Next, that means so CCl4 already explained, boys. Mu is equal to 0. So in this case, that is CHCl3, CH2Cl2, CHCl3. These molecules are all distorted tetrahedral AB4 type molecules. AB4 type molecules. That means finally this concept is useful to predict the shapes of the molecules. Shapes of the molecules. Next one. That is second one. Now, dipole moment mu value and is directly proportional to electron affinity of the element. Very, very, very important, boys. Dipole moment mu is directly proportional to not electronegativity. It is directly proportional to electron affinity of the element. Electron affinity of the element. Let us take different examples. That is CH3F is there, CH3Cl, CH3Br, CH3I. Among these molecules, which one has more mu value? Among these molecules, which one has more mu value? Okay, so which one? Because electronegativity is highest for fluorine, but fluorine has high electron affinity. Therefore, mu order is equal to CH3Cl greater than CH3F greater than CH3Br greater than CH3I. So it is the way to predict the order of different mu values. All these have mu is not equal to 0 only, no doubt. But which one has more, which one has less? That is decided with electron affinity values. Electron affinity. So dipole moment directly proportional to electron affinity. Dipole moment directly proportional to electron affinity. Next case. Mu directly proportional to number of lone pairs on central atom. More is the number of lone pairs, more is the mu value. That means let us take examples. CH4, NH3, H2O. So carbon has no lone pairs, boys, but nitrogen has one lone pair, oxygen has two lone pairs. So therefore mu order N is equal to H2O because it has two lone pairs greater than NH3, it has one lone pair, CH4, it has no lone pair. It has no lone pair. Therefore, highest for water end. So as number of lone pairs at the central atom increases, automatically its mu value increases. Its mu value increases. Next one. Next one, mu value, third one. Mu value is inversely proportional to bond angle. Mu value is inversely proportional to bond angle. Mu value is inversely proportional to bond angle, boys. See here, how is that? That is, fourth point, yes, okay. Mu value is inversely proportional to bond angle. So how, sir? See, let us see examples. For example, organic compounds I am going to consider, boys. Dichloro. It is orthodichlorobenzene. Next, this is metadichlorobenzene. Next, it is paradichlorobenzene. It is paradichlorobenzene. Among these two, 1, 2, 3. Among these three, which one has greater mu value? See, boys, consider the angle between two chlorine atoms. Consider the angle between two chlorine atoms. So this is the nucleus of benzene, boys. So that is why it is the direction. Here it is the theta value. Next, it is the theta value. Next, it is the theta value. So more is the angle. It is almost 60 degrees, boys. It is 120 degrees. It is 180 degrees. More is the angle, less is the mu value. More is the angle. Here almost mu is equal to 0. Here mu not equal to 0. Here also mu not equal to 0. Because so this is in this direction, this is in this direction, mu is equal to 0, cancel it. Mu is equal to 0. So but these two, mu not equal to 0, but which one has more? Which one has more? 1 or 2? Yes, 1 is more, because less is the angle, more is the dipole moment. Therefore, mu order is equal to 1 greater than 2 greater than 3. 1 greater than 2 greater than 3. It is very, very important, boys. It is very, very important. Okay. So it is linear. It has linear structure. Linear momentum is there. Next one. Next one. My question is, in which of the following molecules? Question is, in which of the following molecules mu is equal to 0? In which of the following molecules mu is equal to 0, boys? So note down the questions. Now it is first one, right? Chlorine, para-dichlorobenzene. This is OH, hydroxy. SH, and thioalcohols. This is NO2, dinitro component. NO2. This is NaH2. NaH2. Next. CN, cyanide and cyanide. Boys, please try to identify where mu value is equal to 0. Mu value 0 means, so linear momentum, molecule has linear structure that has mu is equal to 0. Okay, see here, I'm trying it. Chlorine, no other atom, it is the direction, boys. Therefore, mu is equal to 0. So that means this has in this direction, this has in this direction. Single atom, mu is equal to 0. Next. See here. Here OH means this OH at oxide. This is the bond and this is hydrogen. Here also, this OH, this is O, this is H. That means here something angle is there. It is not linear molecule. Therefore, mu is not equal to 0. Mu is not equal. So here only chlorine atom, there is a linear momentum is there, linear molecule, so automatically going to be 0. But it is angular molecule. It is non-linear momentum. Mu is not equal to 0. Next, now here. Similar to OH, oxygen is now replaced with sulfur. That means SH like this SH like this. It has also something angular. Therefore, here also mu not equal to 0. But here NO2, this NO2 like this, N double bond O, A2 bond O. It has a trigonal planar shape. Next, this NO2 also has N double bond O, A2 bond O. Okay, so perfect angles are maintained. Perfect. Here 120. All are 120. Perfect momentum is available. Therefore, mu is equal to 0. Symmetric condition. Yes. Next, NaH2, just like NaH3, pyramidal shape. So that means this NaH2, nitrogen with lone pair. NaH2, nitrogen with lone pair. Therefore, that is non-symmetric end. Therefore, mu not equal to 0, boys. Mu not equal to 0. Now CN, cyanide. Cyanide, the structure of cyanide is like this end. Structure of the cyanide. Cyanide means the carbon is in sp hybridization boys. C triple bond N like this. C triple bond N like this. So this is the direction. This is the direction of dipole moment. It is a linear momentum, symmetric step. Therefore, mu is equal to 0. Therefore, mu is equal to 0. Therefore, how many molecules among these? Mu is equal to 0. 1, 2, 3. These are the 3 molecules having mu value 0. Number of times asked question, boys. Cn means cyanide, like this. Cyanide, a linear grouping, because carbon is in sp hybridization. Sp, wherever sp, that is linear. That is linear. That is why cyanide is like that. That is why linear structure. So overall linear symmetric structure is available. Because of that, mu is equal to 0. Because of that, mu is equal to 0. It is the way to decide. It is the way whether the molecule is polar or non-polar. So mu is equal to 0. Mu is equal to 0, non-polar end. Mu is equal to 0, non-polar end. Mu not equal to 0, those are considered as polar end. Mu not equal to 0, those are considered as polar end. Next, that is see boys, now my question is, just a minute. Cl. It is metadichlorobenzene. Metadichlorobenzene. Next, chlorine. Chlorobenzene. Paradichlorobenzene. Orthodichlorobenzene. Okay. So 1, 2, 3, 4. Among these 4, which pair has same mu value? Which pair has the same mu value? That means 1, 2 or 1, 3 or 2, 3, 2, 4, whatever it may be. A pair has the same lone pair, the same mu value. What is that pair? Yes, Yushwar, you are correct. Only Ishwar corrected. See boys, what is that? Here, this is that momentum boys. These two, this is like this, this is like this. The resulting vector like this. That means these two chlorines behaves like a single chlorine. But that too along this. That means this one also like this side. That means it is with a single chlorine. It is also with a single chlorine. These two have mu same end. But here, that means mu not equal to 0 boys. But here mu is equal to 0. Mu is equal to 0. And there, no doubt, it is in this direction. In this direction, no chlorine is available. But here, in this direction, chlorine is available. That means in this direction, chlorine is available. These two are same boys. Therefore, 1 and 2 have same mu value. Next, similarly, that is CH3, CH3. These two also have same mu value. Same. That means meta-di compounds are in similar dipole moment with single compounds. So that means these two have similar dipole moment values. Very, very, very important, boys. So number of times in your exams ask this type of more problems. Next. As number of chlorines, number of halogen atoms increased, mu value decreased. As number of halogen atoms increased, mu value decreased. So very, very important. That means the same halogen but number increased. For example, CCl4, CHCl3, CH2Cl2, CH3Cl. CH3Cl. So here halogens are same, but number of halogens are different. Therefore, the order of mu order ending, dipole moment order ending. So it is, tell me, yes, fourth one has highest, that is mu CCl4 is less than this one, this one. Okay, the values for that one, here mu is equal to 0. Already I told to you, CCl4 has mu is equal to 0. Second one has 1.01 debye. 1.01 debye. Third one has 1.60 debye ending. Fourth one has 1.87 debye. 1.87 debye. That means as number of halogens increases, mu value decreases. That means the symmetry increases. Okay. Next one, that is here dimethyl compound. Next dichloro compound. Next OH and fluoro compound. So here what we expected, listen carefully, boys. So mu observed and mu calculated value sometimes may be equal to expected value, sometimes is equal to expected value. Here mu experimental value is equal to mu calculated, and with respect to calculation and with respect to experiment, mu values are same. But in second case, mu experimental is less than that of mu calculated. Mu experimental is less than that of mu calculated. In third case, mu experimental is greater than that of mu calculated. Mu experimental is greater than that of mu calculated. Why, sir? Why these deviations are applied? So very, very important, boys. So listen here. That is methyl group. Between methyl and methyl, no attraction and no repulsion. Between these two groups, that means expected value is equal to, that means experimental value is equal to calculated value. No attraction, no repulsion. But here chlorine has 3 pairs of electrons. This chlorine has 3 lone pairs of electrons. This electron pair and this electron pair, there is a repulsion. There is a repulsion between chlorine atoms because lone pairs. Those lone pairs creates repulsions. More is the repulsions. This is what we expected angle, but because of repulsions, there is a new angle is like this. New angle is this one. That means angle increases. Mu value decreases. That means experimental value is less than that of calculated value. Angle because of repulsion. So it is a new angle. This is new angle. Angle because of repulsions, angle increases, automatically the value decreases. That means calculated value with respect to this one, but experimental value like this side. Therefore, mu experimental value is less than that of mu calculated value. But there, see here. Here, hydrogen bonding, next coming out any. So because of hydrogen bonding, I will explain at that time. There is an attraction between fluorine and hydrogen because of hydrogen bond. So that is actually we expected the bond angle is like this. The bond angle is like this. But because of attraction, the new bond angle is like this. Because of attraction. That means the bond angle decrease, theta decrease. Therefore, mu increase. That means the experimental mu should be greater. We calculated like this. But practically, this is the condition. Therefore, experimental mu value is greater than that of calculated mu value. That means all molecules doesn't have as we expected it, their mu values. Because of repulsions and attractive forces, all these are applicable, boys. All these are applicable. These are all some factors. These are all, that is the characteristic properties. We must observe. Next one. Next one, that is, this is used to distinguish cis and trans compounds, isomers. So this mu value is used to distinguish cis trans isomers. What is this cis trans isomers, boys? Cis trans isomers are nothing but, so that is, see boys, there is C double bond C. This carbon has 2 bonds. This carbon has 2 bonds. Okay. Now this is the internuclear, that is C double bond C axis. This is C double bond C axis. So this C double bond C. So here 2 groups are possible, AB groups. Here also AB groups are attached. This carbon contains AB. This carbon also contains AB. If similar groups are on the same side of the C double bond C, this is called as a cis isomer. So for C double bond C compounds, similar groups on the same side of the C double bond C, that is a cis. Similar groups are on the opposite side of the C double bond C, that is a trans. That is a trans. That is a trans. That is, this is A, B, B. So similar groups are on the opposite side of the C double bond C. See here. This is the C double bond C. So this is opposite in direction. Opposite. Both A are opposite. That concept is called as trans isomer. Trans isomer. This is a cis isomer. So generally, mu cis is greater than that of mu trans. That means cis isomers have more dipole moment than that of trans isomer, because these two are opposite. This one is cancelled with this one is cancelled with this one. Sometimes becomes 0 or not equal to 0, but less value is applicable. Mu cis isomer is greater than that of trans isomer. So let us take some examples. So if groups are same, mu is equal to 0. If groups are not same, that means like this. A, B, B, C. Groups are not same. That means this is the direction, mu not equal to 0, but has less value. Mu not equal to 0. Okay. So let us take some examples, boys. Let us take some examples. That is, see here, C double bond C, H and methyl group, This is 1, 2, 3, 4, second carbon double bond. This is 2-butene. But so this is C double bond C. So similar groups are on the same side. That's why it is cis-2-butene. Cis-2-butene. Next, C double bond C, H, CH3, H, CH3. So this is C double bond C axis. So this is 1, 2, 3, 4. So it is also 2-butene, boys. So opposite in sides, therefore trans-2-butene. Trans-2-butene. Here, this methyl group has electron donating tendency, boys. Therefore, the dipole moment is like this. Here also, the dipole moment is like this. The resulting dipole moment in this direction. Exactly opposite way, there is no value in. Therefore, mu not equal to 0. Therefore, mu not equal to 0. But there, this dipole moment is like this. This dipole moment is like this. So that both are in opposite. It is a plus mu, it is a minus mu. So these two are cancelled, therefore mu is equal to 0. Therefore mu is equal to 0. So that means cis isomer has not equal to 0. Trans isomer in this case is equal to 0. In this case is equal to 0. Or sometimes less. Sometimes less. Next. That means more mu, that is the cis isomer, less mu or is equal to 0 mu, is equal to 0 mu, that is trans isomer. Trans isomer. Next, let us take different examples. C double bond C, H, CH3, Cl, H, Cl, H. Okay, it is cis isomer. Next, C double bond C, H, CH3, H, Cl. Boys, it is a trans isomer. In this pair, which one has the greatest mu value? Which one has the greatest mu value? One or two? One or two? See, boys, chlorine in this direction, mu. Methyl group donating nature in this direction. Okay, so it is in this direction. It is in this direction, opposite directions almost. Next, here chlorine in this direction. It is a methyl group in this direction. Both the directions are same directions, boys. Mu enhanced. Mu enhanced. That concept is not applicable here. Therefore, here mu is equal to more. Here mu is equal to less. But mu not equal to 0 here. Here also mu not equal to 0. Therefore, in which case mu is equal to more? Trans case end. That means not always trans has less mu value. So sometimes trans also has. Sometimes trans also has more mu value. This is the best example. In this case, trans has more mu when compared to cis. In this case, this is the way to express whether the compound is cis or trans. Okay, so that is very, very important application. And also the most important application of this dipole moment is useful to predict the percentage ionic nature of the covalent bonds. Mu is used to calculate the percent ionic character of a covalent bond. Mu is used to calculate the percent ionic character of a covalent bond. Boys, already we know that every covalent bond has something percentage ionic nature. No per 100% ionic, no 100% covalent bond exists. So ionic bond has covalent nature, covalent bond has ionic nature. Here covalent bond, how much percentage of ionic nature is there? That percentage of ionic nature is explained on the basis of this mu value. That is the formula, most important formula. Very, very, very important formula. That is percent ionic nature is equal to mu observed by mu calculated into 100 or mu experimental by mu calculated into 100 or mu given by mu calculated into 100. Whatever it may be the formula, that is the same. It is the formula used to calculate percentage ionic nature. Very, very, very important. So mu observed, that means that is the given value. So experimental value. By mu calculated mu calculated with the help of delta into ln. By using this formula, we should calculate mu value. So this is mu calculated. The given value is mu observed. Given value by calculated value into 100. That gives a percentage ionic nature. Let us take a problem, and very, very important problem. Boys, please note down the problem and do along with me and solve along with me. Question: the experimental dipole moment of HCl is 1.03 dBi. The experimental dipole moment of HCl is 1.03 dBi, and its interionic distance is 1.27 angstroms. Calculate the percent ionic nature of HCl bond. Calculate the percent ionic nature of HCl bond. Very, very, very important, boys. Very, very, very important. So first of all, see here, the experimental dipole moment. This is the given value, boys. Mu experimental. Next, interionic distance. Interionic distances means bond length. Nothing but L. This is that L value. Okay. So now he want to calculate percent ionic nature. Percent ionic nature, the formula is mu observed by mu calculated into 100. First of all, I am trying to calculate mu calculated in. So mu calculated is equal to delta into L. The bond is HCl. Chlorine gets partial negative charge, hydrogen gets partial positive charge. That means only -1, only one electron involved here. One electron is lost and one electron is gained in it. Therefore, one electron. Therefore, delta is equal to 1 into 4.8 into 10 power minus 10 ESU1. For example, if H2O is given to you, this one gets partial negative positive charge, this one partial negative positive charge. This one partial positive charge, this one partial negative charge. Here -2 is the partial positive charge. In this case, delta is equal to 2 into 4.8 into 10 power minus 10. So in that case, 2 into H2S, H2O are given to you like that. But it is HCl 1 into 4.8 into 10 power minus 10. This is mu value, and L is equal to distance between these two, that is 1.27 angstroms. That is 1.27 into 10 power minus 8 centimeters. This is ESU, this is the centimeters, boys. So now mu is equal to mu calculated is equal to delta, that is 1 into 4.8 into 10 power minus 10 ESU into L 1.27 into 10 power minus 8 centimeters. That is equal to 4.8 into 1.27 into 10 power minus 18 ESU centimeters. 10 power minus 18 ESU centimeters is nothing but dBi. Therefore, 4.8 into 1.27, that is equal to 6.098. This is mu is equal to 6.09 dBi. It is a mu calculated, our calculated value. Therefore, percent ionic nature is equal to mu observed by mu calculated into 100. That is equal to mu observed or mu experimental. That is 1.03 by calculated value 6.09 into 100. So tell me how much is the answer? That is 16.9%. 16.9. That means HCl ionic nature. HCl bond has 16.9 ionic nature. 16.9% ionic nature. That means that bond has more covalent nature, less is the ionic nature. That means percentage ionic nature is explained on the basis of this dipole moment. 100% tomorrow in your exam, this model problem will appear. 100%, very, very important. Next. That is, so mu is also useful to calculate bond moment of a molecule. Bond moment of a molecule, and mu is also used to calculate bond moment. What is this bond moment, sir? This bond moment, it has units equal to mu value. It has units equal to mu units. That is Debye units, ES to centimeters. So units of mu and bond moment are both are same. So that is, it is almost mu combination. What is this bond moment, sir? That is, bond moment is nothing but the contribution of individual bonds, the contribution of individual bonds in the dipole moment of a polyatomic molecule is the bond moment. So see boys, a polyatomic molecule, let us take H2O. This has this direction bond moment, this has this direction at an angle of theta. That means during calculation mu value, this bond contributes something, this bond contributes this something. That means how much contribution from one bond during calculation of mu value, that is called as bond moment. So with an angle theta. So to calculate this one, mu is equal to that is mu observed experimental is equal to 2 into bond moment into cos theta by 2. Theta is the angle between the two bonds. This is the formula used to calculate bond moment. So mu observed is equal to 2 into bond moment into cos theta by 2. Or sometimes if it is equal to mu 1, it is equal to mu 1. If it is equal to mu 2, dipole moment in this case mu 2, it is mu 1. Therefore, mu is equal to, that is mu observed is equal to under root mu 1 square plus mu 2 square plus 2 mu 1 mu 2 cos theta. This is also the formula, boys. That is, so if mu 1 is the bond moment of this one, if mu 2 is the bond moment of this one. So therefore, mu 1, mu 2 are the bond moments of first bond and second bond. So therefore, mu1 square plus mu2 square plus 2 mu1 mu2 cos theta. Theta is the angle between the two bonds. Theta is the angle between the two bonds. S resulting vector. S. Okay. So now by using this, there is a problem. Please note down that problem also. So this is the final conditioning. This is the conclusion, last topic in dipole moment. That is problem wise, note down it. The dipole moment of H2S is 0.95 dBi. Find the bond moment. Find the bond moment. Find the bond moment of H2S if the bond angle is 97 degrees, given cos 48.5 degrees is equal to 0.661. Cos 48.5 degrees is equal to 0.662. So this is the question, boys, in terms of bond moment. In terms of bond moment. Okay? Yes, correct, boys. That is our calculation. That is mu observed is equal to 2 into bond moment into cos theta by 2. So mu observed, this is the given value, boys. That is 0.95 dBi is equal to 2 into bond moment we have to calculate into cos 97 by 2. That is nothing but this much value. That is 2 into bond moment into 0.662, 0.95. Therefore, bond moment is equal to 0.717 dBi. 0.717 dBi. So very, very important model, boys. Percentage ionic character and bond moment calculation. So every point what we discussed here in dipole moment is very, very, very important. Very, very important. Okay. Now we are entering into the hydrogen bonding, boys. Hydrogen bonding. See here. Hydrogen bonding. What is hydrogen bond? Where it is applied? What are the effects of this hydrogen bond? Hydrogen bond. So first of all, I will explain with an example. After that, I will give the statement. See here, boys. H2O. H2O. So this is H2O molecules in water. In water. Okay. So here oxygen is partial negative charge, it gets partial positive charge. This gets partial positive charge, this one gets partial negative charge. This one also partial positive charge, partial positive charge. So this is one of the water molecules. This is another water molecules in water. In water. Now here, this is the hydrogen connected with, bonded with high electronegative element. Oxygen is high electronegative element, boys. Next, this hydrogen gets partial positive charge. This is nearer to the another high electronegative element. Oxygen is also another high electronegative element, but it has negative charge. Between this negative charge and this positive charge, so there is a weak electrostatic force of attraction. There is a weak electrostatic force of attraction. What is this? This is a weak electrostatic force of attraction. It is the weak electrostatic force of attraction that existing between hydrogen atom of one molecule and high electronegative element of another atom. High electronegative element of another molecule. So there is an attractive force. This attractive force, this weak electrostatic attractive force is called as hydrogen bonding. That is called as hydrogen bonding. So where this hydrogen bonding was between hydrogen atom and high electronegative element. That hydrogen atom must covalently connected with another high electronegative element. So hydrogen atom must be covalently bonded with high electronegative element. That hydrogen gets partial positive charge. So that hydrogen is bonded, weakly attracted with another high electronegative element of the same molecule or different molecules. So that is called as hydrogen bonding. See here, I will explain with one more example. Let us take C2H5OH. It is ethyl alcohol. It is ethyl alcohol molecule. This is ethyl alcohol molecule. Next, water. This is water molecule. Here different molecules. In previous same molecules. Here hydrogen bonded with high electronegative element. This oxygen gets partial negative. This oxygen gets partial positive. This oxygen gets partial negative. This hydrogen gets partial positive. Because of this, there is an attractive force. This attractive force is nothing but weak electrostatic force of attraction, which is also nothing but hydrogen bond. See boys, here one is alcohol molecule, another one is water molecule. But between the molecules, there is attractive force. This weak electrostatic attractive force is nothing but hydrogen. Next, one more example. Let us take boys, this is benzene. Now it is OH. Benzene with OH is called as a phenol. Here is fluorine. That is called as orthofluorophenol. This is same molecule, single molecule, but it is one of the groups, it is another group. Two groups of the same molecule. See here, our condition is applied there. Here hydrogen, which is bonded with high electronegative element. This one gets partial positive charge, this one partial negative charge. Fluorine, high electronegative element. Between these two, there is weak electrostatic force of attraction. That weak electrostatic force of attraction is also called as hydrogen bond. What is the difference between these two? Here, hydrogen bond between two molecules. Here, hydrogen bond between two molecules. Here, hydrogen bond between two groups of the same molecule. Okay, so that means wherever it is possible, within the molecule, between two groups, or between two molecules of the same molecule, same substance, or different substances, different molecules. So whatever it may be, that is the weak electrostatic force of attraction. Okay, so that weak electrostatic force of attraction existing between the molecules or between the two groups, that is between hydrogen and high electronegative element, is called as hydrogen bonding. Now, what is the definition for this hydrogen bonding, boys? See here, what is that? The weak electrostatic attractive force present between hydrogen atom of one molecule and high electronegative atom of the another molecule or within the molecule is the hydrogen bonding. So weak electrostatic attraction between hydrogen atom and high electronegative elements this hydrogen atom must connected with another high electronegative element. That is called as hydrogen bonding, boys. So this hydrogen bonding is two types. Hydrogen bonding two types. This hydrogen bonding is two types. What are those? A hydrogen bond between two molecules or a hydrogen bond within the molecule. So, okay. So those two types are nothing but one is intermolecular hydrogen bonds and the second one is intramolecular hydrogen bonding. So hydrogen bond two types. One is intermolecular hydrogen bonding and the second one is intramolecular hydrogen bonding. So intermolecular hydrogen, inter means between molecules hydrogen bond. This is intermolecular hydrogen bond. This is intermolecular hydrogen bond. A hydrogen bond between the molecules of the same substance or different substance. That is called as intermolecular. That means in water, intermolecular hydrogen bond is there. Between water molecule and alcohol molecule, intermolecular hydrogen bond is there. Intermolecular hydrogen bond is there. But it is within the molecule between two groups. And that means, so this is intra. Intra means same, within. Intra meaning within. Within the molecule, hydrogen bonding. So within the molecule between two groups, hydrogen bond is there. This is intramolecular hydrogen bonding. It is the second type. It is the first type. It is the first type. That means hydrogen bond is how many types, boys? Two types. What are those? Intermolecular hydrogen bonding, intramolecular hydrogen bonding. Okay. What is intermolecular? A hydrogen bond is formed between two molecules of the same substance or different substance. What is intramolecular? A hydrogen bond is formed between two groups of the same substance, same molecule. Two groups of the same molecule. So see, boys, because of intramolecular hydrogen bonding, actually it is open molecule, boys. But after formation of this bond, it is going to be ring structure. That formation of ring is called as chelation. Chelation observed. Chelation means ring formation. That ring formation gives stability of the molecule. Stability of the molecule. Okay. So that means intramolecular hydrogen bond gives chelation. Chelation. Okay. So here intermolecular hydrogen bond, intramolecular hydrogen. So that means it is nothing but a bond. We have covalent bonds, hydrogen bonds, and also van der Waals forces of attraction are there. So between these, which one is strong bond, which one is weak bond? Covalent bond, perfect bond, strong bond. Hydrogen bond, weak bond. Van der Waals forces, weakest attractive force. So among these three, so the order of strength of different bonds is the order of strength of different bonds is covalent bond is stronger than hydrogen bond, which is stronger than van der Waals forces. So that means hydrogen bond is stronger than van der Waals forces but weaker than covalent bond. Hydrogen bond is stronger than van der Waals forces and weaker than covalent bond. So that means hydrogen bond also bonded. Its bond energy is in between 10 to 40 kilojoule per mole. So 10 to 40 kilojoule per mole. So see here. So that means strong hydrogen bond has almost 40 kilojoules of energy. So weak hydrogen bond, strong, weak. Which one is strong bond? Which one is weak hydrogen? So see, boys, hydrogen bond. That means it is between hydrogen atom and high electronegative element. What is that high electronegative element? So generally, electronegative element, high electronegative elements are fluorine, oxygen, and nitrogen. That means it is formed between hydrogen and fluorine. So that means it is formed between hydrogen and oxygen. It is formed between hydrogen and nitrogen. Hydrogen and nitrogen. As electronegativity of the element increases, strength of the bond also increases. That means here this is the strongest hydrogen bond. strongest hydrogen bond. This is weakest hydrogen bond. That means as electronegativity of the element, electronegativity increases. Electronegativity increases. Strength of hydrogen bond also increases. Therefore, HF hydrogen bond is stronger than HO. Hydrogen bond is stronger than HN. HN. So there is a question, boys. So nitrogen electronegativity is equal to 3.0. Chlorine electronegativity is also equal to 3.0. But nitrogen frequently involved in hydrogen bond formation, but chlorine almost very rarely, not in Japan, so rarely involved in hydrogen bonding. Why, sir? Why almost chlorine not involved in hydrogen? Almost chlorine not involved, but sometimes rare occasions involved in hydrogen bonding, because chlorine size is more, hydrogen size is less. That means it has more size than. That is why chlorine almost not involved in hydrogen bond formation. So, but rarely, in some cases, it is applicable. It is involved in hydrogen. So, this is strength of hydrogen bond and some cases. Now, sir. So, what are the effects of this hydrogen bond? This hydrogen bond affects number of physical properties of the elements. Number of physical properties of the element. Okay, what are those, sir? See here. First point, effects. First point, alcohol is soluble in water due to intermolecular hydrogen bonding. Actually, alcohol is organic and water is polar and it is non-polar, it is polar, but alcohol molecules are soluble in water because of intermolecular hydrogen bond. That is already I wrote, that is it is alcohol voice, it is water. Between alcohol molecule and water molecule, so there is intermolecular hydrogen bonding. Because of this intermolecular hydrogen bonding, so alcohol is completely soluble in water. Alcohol is not completely soluble in water. That means, so one case. Second point, glucose is a non-polar substance. Water is a polar substance. Actually, we expected these two are not miscible. Not miscible means not mixed, but glucose is completely soluble in water due to intermolecular hydrogen bonding. Due to intermolecular hydrogen bonding. See, boys, glucose, that is C6H12O6N. It is glucose molecule. That means CHO, COH, H, CH, OH, CH, OH, H, COH, H. It is a CH2OH. It is the glucose molecule, boys, C6H12. Water molecule, this is H2O molecule. So in OH, this is hydrogen attached to high electron element. There is hydrogen bonding. That means because of intermolecular hydrogen bonding, glucose is soluble in water. Glucose is soluble in water. So that means non-soluble substances are soluble because of intermolecular hydrogen bond. That means it affects solubility of the compound. It affects the solubility of the compound. Next, water exists in associated liquid. That is H2O at room temperature exists as liquid, in particular associated liquid. Exists is as liquid, but H2S, same group, sulfur is also same group. H2S is a gas because between H2O molecules, hydrogen bond is there. H2S molecules, hydrogen bond is not there. H2S, sulfur has not that much electronegativity. That means H2O. These are H2O molecules, boys. Between these two, intermolecular hydrogen bonding are possible, and they're like this. That means for water molecule, on average, 2 hydrogen bonds are possible. On average, 2 hydrogen bond molecules. That means one water molecule, one water molecule association takes place. That's why water exists as associated liquid. Water exists as associated liquid. For example, in place of oxygen, sulfur is replaced. That is H2S. H2S. That means sulfur is not that much electronegativity. So hydrogen bond only with nitrogen, oxygen, and fluorine. No other element cannot form hydrogen bond. So sulfur cannot form hydrogen. That means H2S and H2S discrete molecules are there. Discrete molecules. That's why it is in gaseous state. No hydrogen bond existed. No hydrogen bond exists. That's why it is in gaseous state. Therefore, at room temperature, H2O exists as associated liquid because of intermolecular hydrogen bond. H2S is a gas. That means gas molecules are there. That means discrete molecules are there. That's why it is exists in gaseous state. Next 10. That is HF. That means between HF molecules there is strong intermolecular hydrogen bonds are there. Strong intermolecular hydrogen bonds. But H2O, so between H2O, this is H2O. That means it is when compared to this is weakened. Weak hydrogen bond. That means hydrogen bond in water is weaker than that of hydrogen bond in HF. But the boiling point of H2O greater than HF. Why? The boiling point of H2O is greater than that of HF. Even though it is strong. Strong means more energy is required to break this. So more energy means more is the boiling point we expected. But boiling point of water is more than that of HF. Even though hydrogen bond strength is here is more. Why, sir? Because in H2O, reason 1, in H2O, on average, this gives hydrogen bond, this gives with hydrogen bond, this gives hydrogen bond, this one. That means on average per water molecule, 2 hydrogen bonds are possible. But in HF, only 1 hydrogen bond is possible. Only 1 hydrogen bond. That means number of hydrogen bonds here is more than that of here. That means more hydrogen bonds are there. More energy is required to break that bond. That is why hydrogen bond boiling point of water is greater than of HF, even though HF strength is more here. Next, another case. So in vapor state, second point. In vapor stage, H2O exists as discrete molecules. That means each and every molecule is going to be separated. But in vapor stage, HF 6 exists. That means 6 HF molecules unitedly entered into the vapor state. That means only a few HF bonds hydrogen bonds are going to broken. That means HF, 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 HF. So this hydrogen bond, if these are broken, even though these hydrogen bonds are no need to break. That means number of hydrogen bonds are going to break is less in HF than that of H2O. That is why H2O boiling point is more than that of HF. That means, so this hydrogen bond influences intermolecular hydrogen. Intermolecular hydrogen bond increases the boiling point of the chemical. Increases the boiling point of the chemicals. So these are all effects of hydrogen bonding. Next. Boys, listen. So maybe up to 1 I will take the class. Please wait. I want to complete the concepts. Next one. That is next point. Sometimes molecules like HClO4, this is called as perchloric acid, like HClO4, CH3COOH, CH3COOH, nothing but acetic acid, boys, exists as dimers. Dimers means two molecules unite with each other. Exists as a dimers. So as a result, their molecular weights are doubled. This is due to intermolecular hydrogen bonding in that molecules. This is due to intermolecular hydrogen bonding. See, boys, HClO4, Cl, double bond O, OH. It is HClO4. Next, Cl, double bond O, OH. That means it is one HClO4. This is another HClO4. Between two HClO4 molecules, there is intermolecular. Between these two hydrogen bond is possible. This is intermolecular hydrogen bonding. This intermolecular hydrogen bond existing between two HClO4 molecules. That's why these two are united with each other. So two molecules combination is called as a dimer. That's why HClO4 molecule exists as a dimer. Okay. Therefore, so molecular weight is always doubled. So this one plus this one, that's why molecular weight is doubled. Like that, acetic acid also. Acetic acid, CH3. Not only acetic acid, boys, carboxylic acids mostly, particularly acetic acid. CH3COOH. CH3COOH. That is two acetic acid molecules, boys. Here hydrogen bond, here hydrogen bond. So between two molecules, hydrogen bonds, right? It is also intermolecular hydrogen bonding. That means intermolecular hydrogen bonds, molecular association possible, dimerization is possible. Okay, so that is why molecular weights are doubled. So why acetic acid molecule exists as dimer? Because of intermolecular hydrogen bonding. That means inter hydrogen bonding, molecular associations possible. Next, that is water. Sorry, ice. Density of ice is less than that of water. Density of ice less than that of water. It is also due to intermolecular hydrogen bonding in ice. Like this. See, boys, how that ice molecules are associated. Tetrahedral ice molecules, that is H2O, one water molecule, Next, another H2O molecule, another H2O molecule, another H2O molecule. Okay, these are water molecules. So in between there is another water molecule, another water. Between these two, between these two, between these two. So between, just a minute, these two. Okay, so like this, just a minute, I'm writing this one like this. Between these two, hydrogen bonds are possible. Tetrahedral case, boys. This is tetrahedral. That means because of that, empty space, hollow space is there. Because of empty space, density is very, very less. So that means ice density is less than that of water. It is due to tetrahedral structure of ice molecules. Tetrahedral structure of ice molecules, intermolecular hydrogen bonding exists. So that is why density of ice is very, very less. Density of ice is less than. Next one, that is some molecules stability is also possible. So that is, see here, paranitrophenol and also orthonitrophenol. So it has more boiling points, it has low boiling points. Because of more boiling points, less volatile. Volatile means less evaporation. Vaporization is less. Less evaporation means less volatility. Next, low boiling point means more volatility. So this is due to intermolecular hydrogen bonding. It is due to it is intermolecular hydrogen bonding. Intermolecular hydrogen bonding increases the boiling point. Intramolecular hydrogen bonding, increases boiling point. Intramolecular hydrogen bonding decreases the boiling point. That means boiling point is directly proportional to intermolecular hydrogen bonding and inversely proportional to intramolecular hydrogen bonding. So boiling point is inversely proportional to intramolecular hydrogen bonding and directly proportional to intermolecular hydrogen bonding. Because of that, paranitrophenol has more boiling point. Orthonitrophenol, because it has intramolecular hydrogen bonding, this has intermolecular hydrogen bonding. See here. The structures are like this. The structures are like this, boys. NO2, it is OH. It is paranitrophenol. Next, one more. See, boys, this is one paranitrophenol, this is another paranitrophenol. Between these two, here, intermolecular hydrogen bonding. Like this is with another, this is with another. So that means intermolecular hydrogen bonding, molecular association possible. Therefore, boiling point increases, therefore volatility decreases. It is in paranitrophenol. So this is a possibility. Next, I am taking orthonitrophenol. orthonitrophenol. That is, this is orthonitrophenol, boys. Here, between these two groups, hydrogen bonding is phosphoryl. So within the molecule is phosphoryl. Therefore, it is intra-molecular hydrogen bonding. That implies no another molecule is required. That means no molecular association. No molecular association. Therefore, boiling point is less. Therefore, volatility is more. Volatility is more. Therefore, orthonitrophenol has intramolecular hydrogen bonding. Paranitrophenol has intermolecular. Whenever that is intermolecular hydrogen bonds are exist, they have more boiling point. Intramolecular hydrogen bonds, those have less boiling points. Next, these hydrogen bonds increases the stability of the molecules also. Actually, those are we expected less stable, but because of this hydrogen bonding, these have more stability. So see here the example. That means increases the stability of some molecules and stability of some molecules. How is that? See here. Actually, gem dihydroxides, diols and not hydroxides. Gem diholes. Hole means alcohols are not stable. That means a carbon bonded with two OHs. This is a gem dihole. Okay, unstable. But some gem diholes are stable. But some gem diholes are stable due to intramolecular hydrogen bonding. Due to intramolecular hydrogen bonding. See, boys, chloral hydrate examples. Example, chloral hydrate. That is CCl3 CHOH. It is a chloral hydrate. It is an example to gem dihole, but this is OH. This is OH, boys. This is OH, but chlorine is more electronegative. Here it is involved in hydrogen bonding. So this is hydrogen bonding. That is why it is stable. It is stable because of what is this? Intramolecular hydrogen bonding. Because of intramolecular hydrogen bonding, chloral hydrate, even though it is a gem diol, it is more stable. Even though it is gem diol, it is more stable. Next also the compound like this. What is that? That is CF3, C double bond O, COH, CF3. So no doubt here also between fluorine and hydrogen bonds are possible. That's why it is also stable. It is also intramolecular hydrogen bonding. Intramolecular hydrogen bonding. Next, one more example. That is this one. C double bond O. This is a C. OH. It is also gem diol, boys. It is also gem diol. But between these two hydrogen bonds, between these two hydrogen bonds are possible. It is intramolecular hydrogen bonding. It is also stable. So that means intramolecular hydrogen bonding gives a chelation and explains the increases the stability and increases the stability. And last point in this concept, that is hydrated complexes. That is, for example, hydrated complexes. Hydrated compounds. So in these hydrated compounds, that means compounds having water molecules, that is CuSO4 5H2O. CuSO4 5H2O. It is hydrated copper sulfate. See boys, here water molecules are there. How many water molecules? 5. Odd number of water molecules are there. Whenever odd number of water molecules are there, one water molecule is in hydrogen bonding end. One water molecule is in. So whenever odd water molecules are there, one water molecule is in hydrogen bond. For example, even number of water molecules are there, no hydrogen bonding end. Please be conscious. So odd number of water molecules are there, hydrogen bond is there. Even number of water molecules are there, no hydrogen bond end. See here, this is CuSO4 exists as CuH2O 4 times SO4 and H2O. This water molecule is in hydrogen bond with, so between these two, hydrogen bond exists. Between these two, that means the sulfate ion and water molecules, there is hydrogen bond existing. That means wherever odd number water molecules are there in hydrated molecules, in hydrated compounds, odd number is there, automatically hydrogen bond exists. Even number water molecules are there, hydrogen bond not existent. Hydrogen bond not existent. So these are all different conditions in case of hydrogen bonding, boys. Okay, so this is about your hydrogen bonding.